when I circulated the idea and I saw this, I found, well, this is a great idea. I want to participate in it. What can I do? And at that time, I was busy annotating a document in the latest volume of Einstein papers on unified field theory. And I thought, well, unified field theory kind of comes to mind when it's about the problem. And I said, okay, I'll try to say something about that. And then I wrote the title on an abstract, and now I realize it's overly ambitious. So I apologize for that. So I will try to kind of do two things. Do some general things about unified field theory, and then I'll tell you about this interesting document in volume 15 that kind of made me volunteer in this paper, and I'll see how far it goes. And I want to start by really sticking my neck out here with some claims that are probably hard to defend, but I just wanted to kind of, for the sake of the argument. So, the claims are, and I want to be provocative here in my first slide. First, the unified field theories in the 1920s were motivated by some vague philosophical notion of unity of physical fields. What do I mean with vague? Vague, I mean not necessarily to be concretized in very precise terms. Instead, what I mean, I could say negatively, these theories, I think, were not motivated by any inherent conceptual consistency or by difficulties or by the wish to extend somehow the empirical reach of the theories. Instead, they were kind of concretized on the level of a mathematical representation, in particular with respect to finding field equations, generalized field equations for gravitational electromagnetism. And the specifics of the heuristics, and that's part of the vagueness thing, the specifics of the heuristics of the unified field theories derive more or less entirely from the specifics of the mathematical representation. So what's the role left for philosophy in a vague sense also, is sort of only as providing the energy to go along that way without providing direction. So that would be my claim. And you see it's very broad, and I immediately do a disclaimer. I think this is true for many ends, but I'm not prepared to defend it for anybody else except for Einstein. Maybe Weil is an exception. Bracket closed. So what I mean with vague, I want to illustrate with a letter, and also because it's fun. This is a letter by Einstein to his friend Bessel. Sometime late December, late 16, early 17, and the vagueness. So this is apparently in response to an early draft version of a very early version of Hermann Weil's attempt at unified field theory that came out half a year later. And he writes, I first read it in German and then I do the translation. So es scheint, dass Weil mit einer unwichtigen hamiltonischen Funktion gerechnet hat. Mir genügt es bei der Hinzunahme der Gravitation das Elektron nicht erklärt. Die Hinzunahme der Gravitation des Elektron nicht erklärt. Überhaupt ist der Zusammenhang zwischen Gravitation und Elektromagnetismus bis jetzt recht äußerlich. Auch wird es sehr schwer zu glauben, dass something, der Herrgott, die Mühe gab, zwar so ganz wesensverschiedene Zustände des Raumes einzuführen. Hier steckt wahrscheinlich noch ein infernalistischer Witz dahinter, infernalischer Witz dahinter. Ich bemühe mich aber vergeblich etwas zu bessern. Now the fun part is that this thing here is not clear what it means, because it's sich or me or uns. So in the edited version we settled on sich. And then the English translation would be, it seems that Weil did his calculations with an incorrect anatomic function. For me it suffices to know that adding gravitation unfortunately does not explain the electron, while generally the connection between gravitation and electromagnetism is up until now very superficial. Also, I'm having difficulties believing that the Lord would have given of himself the pains of introducing two such essentially different states of space. However, I'm trying in vain to improve anything on this. Now, granted, this is a postcard or a letter to professor and so on, but you know, this is the kind of terminology that you encounter in these explicit justifications of choice values. And you know, so, of course, in that situation in the early 20s, the big paradigm for unification had been electromagnetism. Electrodynamics and Maxwell's theory was, in many respects, a genuine unification of electromagnetic fields, and also a kind of unified optical and electric phenomena. And it also had, you know, direct and drastic empirical consequences or verifications in these electromagnetic waves. So this was kind of the star that people were trying to follow. Now, in the 20s, for the unified field theories, the starting point was, of course, the general theory of relativity. So Einstein had, in 1905, he had created a special theory of relativity. And then 10 years later, he had created the general theory of relativity. Now, both special and general theory of relativity were sort of responses and solutions to critical difficulties and inconsistencies. So the special theory of relativity can solve the problem of the inconsistency between the constancy of velocity of light, the relativity principle of mechanics, and the addition theory of velocities. Likewise, the general theory of relativity solved the problem that with the special principle of relativity, you don't have superluminal velocities, and the Newtonian theory of gravitation is an actual distance theory. So there were severe, deep conflicts, conceptual conflicts that were solved by special and general theory of relativity. And you know, the crucial ingredient for the general theory of relativity was a new mathematics based on the line element, which we see here in a famous page of a notebook by Einstein for the first time in the four-dimensional relativistic context. And the starting point for the business of unified field theories really was the establishment of general theory of relativity in 1915 with Einstein's gravitational field equations, either in this form or in the variational form, in late 1915, after years of struggle with Einstein. Now, this is the history of general relativity is a well-told story, and we know that Einstein had a long, many years taken to come to this theory, and we have a fairly clear view of what these steps involve. There is a succession of gravitational field equations, starting sort of by the from the Poisson equation, and then we have several intermediate steps arriving at the actual gravitational field equations. And especially that notebook here allowed us to reconstruct Einstein's heuristics in the process of discovering gravitational field equations. From that perspective, it looks like in late 1915, early 16, the story has come to an end. But very soon, already in 1917, Einstein felt dissatisfied with the gravitational field equations and added the cosmological term when he was exploring cosmological consequences of the theory. And again, 2 years later, he did something actually more drastic. He he changed that crucial factor of 1/2 to 1/4 in the context of trying to apply this theory in the context of deriving the structure of matter. So apparently, with Einstein at least, in 1915-16, the story was not over. It continued. But the heuristics, as we had seen in 1912-15, sort of head count domain. So there's a new heuristics that Einstein is following, and at least just to give you a brief overview of much of his later work. By 1919, when he started to pick up on unified field theory attempt by Weil, Kaluza, and Eddington, he began a search that would kind of take him to the end of his life, which he never really completed, and which took him, over a number of attempts and approaches. First, picking up on approaches that had originally been advanced by others. 1923 on the F-on theory. Then there's a short interlude where he's trying to solve quantum mechanics by overdetermination. Then in 1925, he has a metric F-on approach. In 1927, again, these trace free equations, similar to the one that we had seen in 1919. Then in 1927, the five-dimensional approach. Again, what Kaluza had already suggested in 1919. Then there is a very an approach that also has a lot of public visibility on disk parallelism. In 31, he had something like semi-vector theory, which is also an attempt to come to grips with quantum physics. Again, a five-dimensional approach in the late 30s. In 1944, a very strange non-local attempt for five vectors, and then the last 10 years without the asymmetric theory. So this is just very briefly succession of attempts by Einstein's part to go beyond the Einstein equations. And of course, it's a challenge for historians to explain. Well, let me put it this way. Many physicists said that nothing came of this, of the attempt of Einstein. And then, of course, you ask yourself as a historian, so how do we explain, Einstein is a clever physicist, how do we explain that he spent 30 years of his life following this approach? So this is a challenge for historians. I'm not going to solve this here, but so just to make some distinctions that are necessary in assessing this, there's I think there's at least three different aspects to the program that one must not confuse, otherwise things get fuzzy. The first aspect is the unification proper of gravitational and electromagnetism. So what does that mean? It means you find some kind of mathematical representation where the two fields, the gravitational and electromagnetic field, appear in some sense in a symmetric way. And some sense, of course, means this has to be specified with a concrete representation. And it also means that the Einstein and the Maxwell equations are somehow contained in the representation as a limiting case. And then this is a part which is a little bit more fuzzy. The unification is not only formal, but there has to be some kind of mixing between the fields. And this is kind of picks up on Maxwellian electrodynamics, where you really have, electric and magnetic fields depending on your state of motion. And the mixing must, of course, be compatible with existing knowledge. And then, well, this is something that you can worry about at the end. Does it also imply new aspects that lead to some empirical new predictions? Now, this is all fine, and this is what we understand as a unification of gravitational electrons proper. But there was also, and this is important not to confuse it, there was also the attempt to account for the structure of matter. It was a very ambitious project at the time. So the equations of the theory should also allow for solutions that were in some sense particle-like. So the field equations should allow for solutions which described in some way localized field configurations that you could understand as a particle, and then also from the field equations the dynamics would follow. So this means there would be spherically symmetric, static, and sort of fall off rapidly at infinity, so they're localized in some sense. And they must, of course, be able to account for the existence of two stable solutions, namely the electron and the proton, and for the mass asymmetry of those. Now, this is already ambitious. And on top of that, there was also, of course, the hope by Einstein that such an interpretation would explain quantum theory. In some sense, generate discreteness by overdetermination or some other ideas. Now, most of the time, these two aspects played a role in an intertwined fashion, and this was too ambitious, actually, at least as far as Einstein is concerned. Now, two comments. One is, an expression that Henry Clark used, which I find very useful for this. He called the period in the 20s the two-particle paradigm. Why is that so? Because in the 1920s, that is, say, up until the anti-neutron, the muon or so, there's really only two particles. There's the electron and there's the proton. Okay, there's the proton and the neutron. They have the same mass. They don't have the charge. But really, if you think about it, if the program of unified field theory implies involves that we also hope to be able to explain matter, the structure of matter, it seems crazy to us now, but at that time it was only you had to explain two particles up until this. So that's the two-particle paradigm, which makes it less crazy than it seems to be. The other thing is, going back to the first aspect, that we have Einstein's and Maxwell's equations. So the Einstein equations look like this. The Maxwell equations, probably those of you who have worked on this know them more in this form, but they can be written very compactly. If you introduce a field tensor in this form, they can be written in this way. And then you see, well, this equation here, G equals T, is very similar to that. And this way of rephrasing mathematically on the basis of the representation, the Maxwell equation, in a way that kind of gives the possibility of a structural link to gravitation theory and general relativity, was of course one of the premises for the entire program. Okay, so now I'm to the second part. Now I want to kind of focus on this specific episode that I was working at the time when I thought about joining this symposium. So this is our latest volume of the Einstein Papers, volume 13. It covers the year of January 1922 to March 1923. And the big event in that period of time is Einstein's first trip to Japan. It's his first. It's a long journey that takes from October 22 to March 23, and it has all kinds of interesting aspects, political and cultural and scientific, so on his way he's awarded the Nobel Prize and things like that. I want to focus on the fact that on his trip he spends each way several weeks on board the steamer, and he's sort of away from busy Berlin, where Father Abraham had been assassinated, and things are crazy. So he's on board the ship, the steamer. On the long way from Marseille all the way to Japan and back, each leg was a trip of 6 weeks. And these periods on board the ship, he's basically out of context. He doesn't have meetings, other worries. And what he's doing is he's picking up on his unified field theory ideas again. And on his way back from Japan, he drafts a paper which he finishes here in Shanghai. No, here and then it's almost done, but then he he realizes there's a problem with it. And in his diary, we have all kinds of calculations that apparently we can reconstruct as responses to the problem that he realized here. And then when he is in Suez, he has a revised version that is in a sense of publication. So this is really sort of a laboratory where you can study mathematics of words and how he thinks, and where you have a chance maybe to see what the heuristics were working in the dynamics of his development of the theory. So I want to spend the rest of the talk to give you an idea of what I think we can learn from a detailed analysis of this manuscript, and make you understand why I kind of made these positive claims in the beginning, right? Because here you can really see the constraints and the workings of the mathematical representation when they're being manipulated in a situation where you're actually sitting calculating without distraction from inside. So two things one has to ask in advance. On a trip like this, it's the question: if you go on your own on an island for half a year, what kind of books do you take along? And here again, it's a trip of several weeks, and you can't have so much. So it's like, what kind of books do you take along? We don't have enough, a lot of information, but at least mentally, I think you should put on these two books. The fifth final edition of Common Violent Space-Time Matter, which was maybe just completed early enough to take along, maybe at least some proof sheets. And Eddington's Mathematical Theory of Relativity, again, the preface is dated August. You might have had a chance to pick up that book on this trip. And both Weil and Eddington had advanced approaches for the unified field theory that he was kind of pondering on and pick up on. In case of Eddington's approach, we know that he was thinking about this because he had met Eddington a year earlier in 21, and Eddington had told him about this his paper we were speaking about Friday night in correspondence. And then we have the diary that Einstein writes on board the ship. And from the entries in the diary, we see, this is all localized in time from the day he enters the boat on his way back, December 30, and it's 3 weeks' time, January 22. So it's a peaceful trip. He has an idea of intelligence. He's pondering on calculations. He has a new idea. He's thinking. He's writing a paper. And now I believe I finally understand. This is 10 January. And then 3 days later, he discovered a fly in my electricity ointment. And he has looked at pity, true philosophy, new ideas, discipline, toiling, final drafts. And these 10 days, I think we have documented as calculations in the back of the diary. And so the challenge then, of course, is to reconstruct this. And here's the point that I want to make. The point I want to make is that you have the situation now that Einstein has a general, let me say, vague idea that he wants to unify electricity and gravitation. And he's kind of working with Weil and Eddington. And he has an idea how to kind of concretize this on a representational level, and testing, and the mathematics guides him along. And he's happy with it, and then he discovers, on further thinking, he discovers an internal inconsistency, and then it's interesting because then he has to reflect back. What's the problem in the mathematics? What do I have to check? What do I have to kind of give up? What premises are maybe not so natural, and so on. And this is a process that we, I think, can understand. And there you see the constraints at work that guide the direction of this thing. And so this is the argument I want to make on the next few slides. So what happens here? he has in this upper third are the equations of general relativity of the theory of gravitation. They're based on the metric. You have the Christoffel symbols, you have the Ritchie tensor, you have then the Einstein equations. So this is the theory of gravitation. In the middle third, you have the electromagnetic potential, and from them the fields, and you can write the Maxwell equations in this very compact form, as I showed earlier. You also have currents written in this way, and it's an important fact that, first of all, so this is sort of gravitation, and this is electromagnetism. Now, the Maxwell theory of electromagnetism has this feature that it allows the fact that you have fields without currents. So in a vacuum, you have fields. There are vacuum solutions, so non-trivial waves. And this is a direct consequence of the Maxwell equation. Anyhow, so there is now a variational formulation which sort of combines these two theories. So you can write this as a variational principle. And then the Lagrangian here sort of combines a term from the gravitation and one from the electromagnetism. And then if you do the variation with respect to the metric, you get these equations. So if you do the variation with respect to the fields, you get the Maxwell equation. So you have sort of the formulation of gravitation, of the gravitational field and the electromagnetic field that looks very compact, but this is what he calls äußerlich. That's just the sum of terms. So the idea that he's following up is captured on this slide. So Eddington's idea was to split, to make a differentiation between the metric and the connection. So now you have these things independently given, in addition to the metric. And if you have these independently given, then the Ritchie tensor can be split in a way that allows you to kind of take an anti-symmetric part and directly assume that it has the electromagnetic field. Fine, it's just a differentiation on the basis of the representation. You differentiate things that belong together in the first place now as two independent quantities and try to go along with that. And he does the same thing. He takes a variational principle where he kind of introduces a function that depends on these two quantities independently. And if he applies the machinery, variation with respect to the metric gives him the vacuum gravitational equation, and variation with respect to these things give them compatibility conditions. And this is the thing that in modern theory is done routinely as a Palatini method to derive the connection between the metric and the connection in the Levi-Civita case. But if he does that now in the case where he adds this thing, he gets the Einstein equations all right, but then he gets this additional thing, and he realizes at some point that this condition, which kind of flows out of the representation, it kind of comes out of the calculation, if you interpret this physically again, it means that you define the fields in terms of currents in a way that if you have no currents, you have no fields. So that's the contradiction. And this is how it looks in the manuscript. So this is his diary on board ship, where he's kind of calculating, he's following rules. He's doing the equations, following the manipulations. And here we see him, this derivation that we now call the Palatini method. And here he reacts to he discovers the difficulty and reacts to it by introducing further conception. Okay, this is just to give you an impression of what I mean by the constraints of the mathematical representation. Obviously, I can't explain this in any more detail. But what he ends up with is a paper where he's kind of rewriting his theory. And here you find the motivation again. So it's all based on the metric. And then he says, in wegen der Wahrheitskomponenten des Feldes Wesensfremde. So, Wesensfremde, the electromagnetic potentials were wesensfremde to the metric. And then he says, the wish, the gravitational field and the electromagnetic field, to comprehend this as unity, to have dominates in the last year's theoreticians. So he has 4 more papers, and here's my final slide. I will send you the proofs of my paper, which I must publish by all means, because Eddington's thought needs necessarily to be followed through to the very end. I also now believe that all these attempts on a purely formal basis will not advance the understanding of physics. Maybe field theory has given everything it can give. So that's the end of that approach, but the next one's coming up. And
thanks very much. So for those of you who might have come in a few minutes late, the ground rules are 30 minutes for each speaker. Then Helge will give us his commentary, and then we'll have questions for the 3 of them individually or all together at the very end. So the next speaker is Aaron Wright from the University of Toronto, and Aaron's title is Everything from Nothing, John Archibald Wheeler's Metaphysics of the Vacuum. That would be interesting too. Not today.
there. Fine, and I'll just see if this works. It does. Excellent. Well, some of the formatting may be a little off. But we'll see. So thanks everyone for coming, and as co-organizer of this session, allow me to thank my other co-organizer, Yunara Silva, and all our participants for what has been, and I think will continue to be, very stimulating sessions. So I'm talking about nothing, and well, what is nothing, right? Everyone would agree, physicists and lay people alike, that if one speaks about the space between the stars, or a metal tube pumped free of air, that one has a vacuum. But physicists have a strange conception of what the vacuum is and has been, right? And they differ depending on which community of physicists you're interested in studying. So in general relativity, for example, empty space is empty space, but it can have properties like curvature, it can expand, it can contract, it can push on things, if it has this vacuum energy. This seems more like a substance than like nothing. And then for quantum theorists, though this picture has changed over time, at sometimes nothingness, the vacuum, was a boiling sea of particles that constantly pop into existence in pairs and then annihilate one another again. So this talk is based on a chapter of my dissertation in progress entitled More Than Nothing, Histories of the Vacuum in Theoretical Physics, from 1927 to 1980. And it traces the views of physicists on the vacuum through the communities of practitioners of both quantum field theory and general relativity. Major figures in the dissertation include Dirac, Schwinger, Feynman, Fox, Zeldovich, Penrose, Coleman, and the subject of this talk, John Archibald Wheeler. In addition to this sort of subject, it's also animated by a historical philosophical question. What is the relationship between physicists' ontologies and their epistemologies? What was the relationship between how physicists came to know the world and what they thought the world was made of? I'm not searching for a monolithic answer to this question, but rather a picture of how different interrelationships were at play for different physicists in different times. For the case of Wheeler, I will argue that his epistemic strategies led his ontologies. His rules for investigating nature determine the path of his physical pictures. The main evidence for this is that Wheeler's epistemic strategies remained a constant over time, while his ontological pictures changed. I will elaborate this afterwards, after a brief introduction to Wheeler's life in physics. Here is John Archibald Wheeler. He was a physicist with a vast range. He graduated from Johns Hopkins and began his career in nuclear physics. As we heard yesterday, quite a
a bit about Bohr and his institute. He took a postdoctoral position at Bohr's Institute in Copenhagen in the 1930s, and actually continued his work with Bohr into the post-war period. In the 1930s, Wheeler invented the S-matrix approach to nuclear scattering problems, which would become extremely influential, and collaborated with Bohr on the liquid drop model of the nucleus. After a brief stay at the University of North Carolina, Chapel Hill, Wheeler moved to Princeton in 1938, where he stayed until 76. At Princeton, he was a prolific dissertation advisor. His students included Hugh Everett, who we heard a little bit about in Olival's presentation, and Richard Feynman. Wheeler joined the American war effort at the Hanford reactor site in Washington State, where he acted as liaison between the federal government